And yet, yeah, I know, I'm like, why can't I fall asleep? I'm tired, and yet.
So you're physically exhausted, but mentally it takes someone shut the power button on.
Yeah, that's just so annoying.
Yeah.
Yeah. Man, where's the switch? Yep.
It's like a slow computer which takes time to shut down.
Yeah, much too slow. It's like humming in the shutdown sequence.
Yep.
All right, so let's continue on our merry way here. So last time, of course, we were talking about adiabatic processes versus, because we wanted to say, okay, how fast will the bubble cool as it's rising? And we found that Cp was Cv plus here until the R. And we're going to keep going from there. Adiabatic process. We know that means dq is 0. There's no heat flow in or out. So in that case, we have that all the change in the internal energy is due to the pressure volume work. There's no dq contribution to du, so du is minus pdv. But an adiabatic process, it's still the ideal gas law is applying to our gas as well. So from the ideal gas law with constant n tilde mu, we'll have, so we know that PV is mu RT, PV is n tilde RT. So let's take differentials on both sides. So that says that PdV plus VdP is, if n tilde is constant, then only dt is going to change on the other side. So n tilde R dt.
Oh, and product rule on the left.
What's that? Yeah, the product rule, right. We use the product rule to differentiate the left-hand side. But then remember, we also said that du is always Cv times dt. And so we can say that dt is therefore du over Cv. That's always true. But here, we can say that since du is minus pdv for an adiabatic process, we've got another thing we can say.
Negative
That's right. Minus pdv over cv. That's where we're bringing in that this is an adiabatic process. So we've got a relationship then between dt and dv here that holds. So we can put that into the right-hand side of our prior relationship there. So pdv plus vdp is always n tilde r dt, but if it's adiabatic, dt is minus pdv over cv, so that gives us a relation that we can exploit. pdv plus vdp is equal to minus n tilde r over CV times PdV. And so now we can bring the PD, wow. We can bring the PDVs and let me, that should not have caused anything to happen to the recording, but let me just double check that. Seems to still be going there. So now we can bring the PDVs together on one side and put the PDV on the other side. So P times the quantity 1 plus n tilde r over CV times dV is minus V dV. So let's rewrite that as
separable differential equation.
what's that? That's essentially a separable. Yep, that's exactly right. Yep. And so now we can say CV plus n tilde r over CV times dV over V is minus dP over P, and in fact now we have separated the differential equation. We put V terms on one side, P terms on the other side. But notice that what we got before was that the specific heat at constant pressure was in fact CV plus n tilde R. And so Cp over Cv is gamma. So we can say that gamma dV over V is minus dP over V. And 2, 4, 6, 8 is no time to integrate. So on the left-hand side, that gives us gamma times the natural logarithm of V. And on the right-hand side, that gives us minus the natural logarithm of P plus some constant of integration, which I'll call A. And then we can use, right, we can figure out what it is. So, in principle, it really comes from knowing what the entropy is. So, we're just going to kind of leave it unspecified. So now let's exponentiate. So first we integrate, now we exponentiate. So 2, 4, 6, 8 times 2 exponentiate. So if I do e to the gamma log v, that's the same thing as
E to the log V to the gamma.
exactly. So in other words, it's v to the gamma. So we have v to the gamma is equal to e to the a times 1 over p, because e to the minus log p is 1 over e to the log p is 1 over p. So we can say that P V to the gamma is equal to, we'll call it big K, where K is e to the a, so why not just call it another name? Let's call it K. K is a constant, that depends on the entropy of the gas. And this is the adiabatic gas law. And another way to put it is, because it's not always particularly useful to figure out what K is, another way to think of this is that as the pressure and volume change, P1 V1 to the gamma is P2 V2 to the gamma. So if the pressure, if you have an initial pressure and volume, and you know what the final pressure is, you also know what the final volume is. Is the idea there. The pressure and the volume are linked together such that their product PV to the gamma stays constant as the gas expands or contracts due to changing pressures in the surroundings. Now, V remembers the specific volume, the volume per unit mass. Let's put it in terms of the density, which is the reciprocal of that. The specific volume, volume per kilogram, cubic meters per kilogram, is the reciprocal of the kilograms per cubic meter, 1 over rho. So we can also put this in terms of P rho to the minus gamma is equal to the constant. Or in other words, P is a constant times rho to the gamma. That's another way to express the adiabatic gas law. And always keep in mind, it's not different from the ideal gas law. It still obeys the ideal gas law. This is just an additional constraint on the behavior of the gas. We use the ideal gas law as part of the derivation of this. So
it still depends on.
So it still obeys the ideal gas law. But if the changes are adiabatic, in addition, P is K rho to the gamma. There's a specific relationship between.
Would you call this a special case?
You could, yeah, you could. Essentially, without this condition, you've got 3 variables that can change: pressure, rho, pressure and specific volume or density, P, rho, and T, right? And if it's adiabatic, T is constrained to change such that the pressure is a constant times the density to the power of the specific heats. Gamma, remember, is Cp over Cv, which is 5/3 for a monatomic ideal gas, and so it's typically the value that we'll be interested in. And then your book does it a little bit more roundabout than this, but I think the easiest way to do this is what I'm going to do. So let's take logarithms of both sides. So if P is K rho to the gamma, then the natural logarithm of P is the natural logarithm of K plus gamma times the natural logarithm of rho. And so if we differentiate with respect to R, because our bubble is changing its radius, so let's take DER of both sides, and note that d log PER, for example, is 1 over P dPER, etc. So we're going to do that with the other ones too. with rho too. So d log PDR is 1 over p PDR because, in other words, if you don't see that immediately, if you use the chain rule, that's d log PdP
Oh yeah, it's
PDR,
implicit.
and the derivative of log p is 1 over p.
It's implicitly differentiating MNP.
Yeah, so we're just using the fact that the chain rule says the derivative of log, the log of the function, basically the natural logarithm is the function whose derivative is the reciprocal of the independent variable. So d log p is 1 over p. So what we find then is 1 over p dpdr. Well, this is a constant, so its derivative is 0, is equal to gamma times 1 over rho d rho dr. This is for our bubble. As it changes its rate, as it changes its distance from the center, as it rises, 1 over p dpdr is gamma times 1 over rho d rho dr. That's because it's adiabatic. And the adiabatic gas. But it still obeys the ideal gas law too. So let's write the ideal gas law. As P equals, the ideal gas law P equals rho KT over mu MH. As by taking logarithms of it. So what I'm really trying to say is I'm going to take logs of both sides of the ideal gas law. So we can say, okay, log P is equal to log rho plus log T plus log of K over mu MH. Might as well keep those constants together with one another, so I just group those all together.
This is a natural log, right?
Natural log, right? ln, so natural logarithm. Yeah, it's not log. Take the logarithms. You're just gonna get totally weird, right? So here we've got the lunar rhythm. Oh no, that's not. There's no mirror in there anymore. I wanted to have the lunar rhythm. Oh well. So anyway. So if the mean molecular weight is constant, again that means no change in ionization. Well, then we can say, by taking derivatives again, that 1 over p dpdr is equal to 1 over rho d rho dr plus 1 over t dt dr, and then the constants don't differentiate because mu is constant. If mu wasn't constant, there would be a contribution from that as well.
So that just goes to 0.
So that derivative is 0,
Yeah,
right?
exactly.
So if the ionization is changing, we have another term.
So in this, since we're assuming mu to be a constant?
We are. We're assuming mu to be a constant, and that means the ionization isn't changing, because if atoms stay, if it's rising, it's cooling, so electrons might recombine with atoms. That'll reduce the number of particles, and so that in and of itself will change the pressure, because P is nkt, and so N would go down. N is rho over mu mh, so in other words, the mean molecular weight goes down if you change the number of particles by having electrons combine be stripped off of anything. The mean molecular weight, if you strip an electron off, now you haven't changed the mass really. There's a very slight change due to the binding energy, but you essentially haven't changed the mass, but you've increased the number of particles if you strip electrons off, and so the average mass per particle changes. Because remember, particle here means something moving freely.
Yeah, I remember
In the gas, right,
exercise
yeah.
with the.
Right, so for these purposes, a helium atom, for example, is one particle. It's not six particles. It's, yeah, neutral helium atom is one particle. An ionized helium, each, you have one, if it's singly ionized, there's two particles per helium. One electron and one positively charged helium still has an electron attached. And so change the mean molecular weight if you did that. So constant mu is the same thing as saying the ionization level isn't changing.
In a star, how well does that cause?
So what it means is it works except when you're in an ionization zone. So in other words, for helium, if the bubble's temperature isn't moving through like 15,000 Kelvin or 40,000 Kelvin, where helium goes from being neutral to singly ionized and then singly ionized to doubly ionized, if it's in a region where it's in between, well in between 15,000 Kelvin and 40,000 Kelvin, or cooler than 15,000 Kelvin, or a lot hotter than 40,000 Kelvin, its ionization state will be changing. But I'm going to mention that, in fact, if you're in an ionization zone, then as the bubble rises, it will change its ionization. And that'll help, but the ionization zones tend to be associated with convection because a rising bubble has electrons recombining with atoms. That gives off energy, which keeps the bubble warmer, which helps keep it less dense than its surroundings, which encourages convection.
I see.
So in fact, convection in the stars tends to be associated with ionization zones is what it comes down to.
That's true.
And it'll happen outside them too, but in other words, we typically find that the base of the convective zone is is in an ionization zone because it encourages convection there. So put another way, we can say that dPdr is P over rho, just multiply through by P over rho rho dr plus P over T TdR. But P over rho dr is 1 over gamma dPdr for an adiabatic process. That's what we had just obtained before. Before we had that 1 over P dPdr is gamma 1 over rho dr. So in other words, P over rho d rho dr is 1 over gamma times dPdr is another way to rewrite this expression. So now if we solve for dTdr, what this says is that the adiabatic temperature gradient, the rate of change of temperature with distance from the center of the star for an adiabatically rising bubble, dTdr adiabatic, is equal to 1 minus 1 over gamma times T over P dPdr. So in other words, I just brought multiply it through by T over P.
That's pretty cool.
Mm-hmm. But now we can keep going because, again, the ideal gas law says P is rho KT over mu mH. So that says P over T, sorry, T over P is what I want. T over P, because that's what we got over there. T over P is equal to mu mH over rho times the Boltzmann constant. That's the little k, not the big K from the adiabatic gas law. And from hydrostatic equilibrium, because our rising bubble has surroundings that are described by hydrostatic equilibrium. So it itself isn't in hydrostatic equilibrium because it's rising. Hydrostatic equilibrium would be just sitting there, but the surroundings that it's rising into should be in hydrostatic equilibrium. So, and from hydrostatic equilibrium, of the surroundings, we know that dPdr is equal to minus rho times g m sub r over r squared. This was dPdr is minus rho times the local acceleration due to gravity. And we can use the pressure in the surroundings for the pressure of the bubble, because remember that the pressure of the bubble stays equal to the pressure of the surroundings. We call it E bubble equals P surroundings. So we can, this is legit to use this to apply it to the bubble. So we put in our expression for T over P and for dPdr over here. And that gives us, finally, the equation for B.
Wow.
The thing we've been after, the adiabatic temperature gradient. dTdr adiabatic is equal to minus 1 minus 1 over gamma times mu mH over K times G m sub r over r squared. So there it is, equation 4b. 4a didn't take nearly as long to come up with as 4b did. But that's because convection is more subtle, if you will.
Doctor,
Yeah.
where did the negative rho go?
A minus sign here because of that.
I see that, but where did the rho go?
It canceled out because T over P has 1 over rho in it, and dPdr has rho in it, so rho canceled out for us. That was nice of it.
That was nice, yeah.
Yeah.
Get rid of the density
Yeah,
difference.
it's nice of it. recall that we said that if convection is occurring, it can be shown that the TDR, remember we said, is only slightly super adiabatic. And so we'll just use 4b as the temperature gradient under that condition when there's convection. Not quite right, but it's almost right. And might as well throw in 4a when there's not, when it's radiative. When the energy transport is radiative, the temperature gradient will be 4a. When it's convective, it'll be 4b. Energy transport is via radiative diffusion. But notice also we haven't said, we found out what the adiabatic temperature gradient is, but we haven't said how do you tell whether it's convection or radiative diffusion that is carrying it. So that's the next thing we have to do, is to write down what's the condition that convection takes over.
The tipping point between.
Yeah, where's the tipping point? So you could say, remember that we did say, we've implicitly said, we said that the adiabatic gradient needs to be, what is it? The adiabatic gradient needs to be less steep than the radiative gradient, so that the bubble cools down more slowly. So in principle, you could say, okay, I'll calculate dTdr if it's radiative and dTdr if it's adiabatic, and then decide which it is by comparing those two things.
Yeah, maybe take the absolute value.
Right, but there's a better way. There's a more compact way to do it.
Yeah,
So,
because this would be kind of hard to go through the math.
yeah. So let's talk about what we kind of really look for here, and then what it comes down to is I'm going to have you do a homework problem where it's based on a code called ASTR that the authors of the book developed, and I'll have you use a spreadsheet to stepwise integrate. Well, actually, to check that ASTR is giving essentially correct approximate solutions to the equations of stellar structure. So. Let's develop a more compact way to write the condition for convection. We've already said this. We know the temperature gradient is negative, that it gets cooler as you move away from the star center. And we put it in terms of then, if the adiabatic gradient, if the actual temperature gradient's magnitude is steeper than the magnitude of the adiabatic gradient, then that means the surroundings cool down faster than the bubble does as it rises, and it keeps going. because these are both negative, when you take off the absolute value, the arrow points in the other direction. Does that make sense to you? Yeah.
Since I have one question though, since both of them are negative, and when you remove the absolute value, the sign flips. So it's negative DTDR actual less than negative DTDR adiabatic. If you were to multiply throughout the inequality by a minus sign, would that not give like the same expression as now, but with
If you multiply it by a minus sign, it flips the direction of the inequality. I mean, for example, minus 5 is less than minus 2, right?
So if you
5 is greater than 2. If you multiply through by minus 1, that's equivalent to, if they're both negative, taking off the absolute value sign, and that flips the direction of the inequality.
That's all I needed to check.
Yeah, that's just universally true. It's just a rule. It's always going to hold. Now, of course, it's easy to forget that, sometimes, the absolute value is minus the number. No, that's not true. The absolute value is minus the number only if the number is negative. It's the number if the number is positive, right? So which way you go, right? The absolute value of x is x if x is greater than 0, and it's minus x if x is less than 0. Yeah. And it can be computed. Wait, it's minus x, I thought it had to be positive. Yeah, which it is if x itself is negative. Minus is plus.
They define the absolute value as a stepwise function.
Yeah, it's a stepwise function. That's absolutely right. Yes.
I liked it. When I saw it that way, it made so much more sense.
Yeah.
Other.
I mean, the plot looks like that. It's got a corner point at the origin. So, and that's why, for example, when we're defining things, when in probability and statistics and all that, you use standard deviation instead of absolute value of the deviation. You don't use the average absolute value of the deviation. You use the root mean square deviation because of that corner point, because it makes the function undifferentiable at the origin, and that would make it a lot harder.
Because there's no derivative.
Yeah, because it's got a corner point there. The derivative is undefined at the origin. But that's not true for some of the squares of the deviations. So because of the fact that they're both negative, then the condition is, if you just put it in terms of the gradients themselves, the actual temperature gradient is less than the adiabatic gradient. It's more negative than the adiabatic gradient. Since they're both negative,